Welcome to the deep dive. We sift through the noise, pull out the essentials, and hopefully turn that information overload into a few aha moments for you.
And today, we're diving into something that's, well, really changed the game in human spaceflight.
Exactly. Did you know the whole way astronauts get to the International Space Station has fundamentally shifted, like just in the last few years?
It's not just NASA or Roscosmos building and launching their own stuff anymore.
Right. For decades, space travel was all about these big national efforts, countries doing their own thing.
But now, we're in a totally new era, largely thanks to things like the Commercial Crew Program, or CCP.
You've got private companies really stepping up to the plate, taking the lead and getting astronauts to orbit.
It's a huge shift.
And that is exactly what this deep dive is all about. Our mission today is to unpack it all. The key players, the amazing spacecraft they've built.
And the, maybe less obvious, philosophies behind it all, this new chapter.
Yeah, we've got some great sources to dig into: program details, astronaut accounts, the works.
So the big question we're really wrestling with here is, what does it actually mean when private companies take over human spaceflight?
And yeah, how does that change the job, the very role of an astronaut?
Let's start at the beginning, the why.
Okay, so let's rewind a bit. Back in 2011, a pretty major thing happened. NASA retired the space shuttle. Iconic program, gone.
Absolutely. And that immediately created this gap, a really critical one.
Suddenly, NASA didn't have its own ride to the ISS.
Nope. They found themselves, for the first time really, completely reliant on Russia's Soyuz program to get astronauts up there and back.
Which, worked, but it created this dependency.
A dependency NASA was understandably very keen to end, and pretty quickly.
So enter the Commercial Crew Program, CCP, kicked off in 2011.
And this was radical, a real departure. NASA shifted from, designing and building its own vehicles.
Like they always had done.
Right, to basically contracting out the taxi service to the ISS using commercial companies.
It really sparked a competition, didn't it?
Yeah. Oh, definitely. NASA put significant money into the early development rounds to deliberately foster that competition.
You had programs like CCDev, Commercial Crew Development. That was more about early concepts, right?
Yeah, refining ideas. And then CCCAP, Commercial Crew, integrated capability, which funded the more, let's say, mature designs.
And some big names emerged there. Boeing with their Starliner capsule.
They got some hefty initial awards, $92.3 million in CCDev-2, then another $460 million in CCCAP.
And SpaceX with Crew Dragon, they weren't far behind.
No, they got $75 million in CCDev-2 and $440 million in CCCAP. So similar ballpark early on.
But it wasn't just a two-horse race initially, was it?
Not at all. You had other serious players in the mix. Sierra Nevada was developing their Dream Chaser spaceplane.
Looked really cool.
It did. And Blue Origin was involved too.
Yeah.
But in 2014, NASA made the final call.
They awarded these big fixed-price contracts, $4.2 billion to Boeing.
And $2.6 billion to SpaceX.
Which was quite a difference in funding, actually.
It was. And Sierra Nevada, they actually protested that decision, though that protest was ultimately declined.
So that 2014 selection really set the course.
Absolutely. And it tells you a lot about NASA's goals. They wanted cheaper access to the ISS, more reliable access.
And crucially, they wanted to kickstart a whole new commercial space industry, a market, really.
Exactly. While making sure the U.S. always had its own way to get people to space, diversify the options, create a more robust, maybe more innovative ecosystem.
Okay, so out of all of that, we end up with these two main vehicles, SpaceX's Crew Dragon and Boeing's CST-100 Starliner.
The workhorses, yeah.
And while they look different, took different paths, they both had to meet some fundamental NASA requirements. Maybe let's start with what they have in common.
Good idea. Because despite the differences, NASA set some clear ground rules. Both capsules, for instance, are designed to dock autonomously with the ISS.
Hands-off docking, mostly.
Right. But they both have manual override capabilities using touchscreens, interestingly. A very modern approach compared to, walls of switches.
Yeah, definitely feels new space. And safety, that had to be paramount.
Oh, absolutely non-negotiable. Both vehicles had to meet this incredibly tough NASA safety standard. A 1 in 270 chance of catastrophic failure during ascent or reentry.
And just for context, the shuttle was rated at about 1 in 90.
So a huge improvement, a massive focus on astronaut safety, building on lessons learned over decades.
What else? They both have to stay docked for a while, right?
Yep, certified for up to 210 days docked to the ISS. That covers your standard 6-month crew rotation with some margin.
And they use the same docking port standard.
Correct. The International Docking System Standard, IDSS, ensures they can both connect to the station's available ports.
And crew size. NASA sends 4.
Typically 4 astronauts per NASA mission, yeah. Though technically both capsules could probably fit up to 7. NASA just contracts for 4, usually, maybe with a 5th seat available sometimes. And inside, they offer about the same amount of space, around 11 cubic meters or 390 cubic feet of pressurized volume, which is, your living and working area.
Okay, so same basic rules, but very different approaches. Let's talk Crew Dragon first. SpaceX. Reusability is their big thing.
It really is. It's core to their whole philosophy.
Yeah.
The capsule itself. It's 3.7 meters wide, about 4.4 meters tall, without the trunk section.
And the trunk adds a bit more length.
Yeah, brings it to 7.2 meters total. But the revolutionary part is the crew cabin itself. It's designed to be reused many times.
How many times are we talking?
Initially, NASA certified it for 5 flights, but SpaceX is pushing that boundary. They're working now to certify it for up to 15 flights.
15? Wow. That's key to getting the cost down, presumably.
That's the entire strategy. Drive down that per-seat cost through high reuse. The trunk section, though the part with solar panels and radiators that is expendable, ditched after each flight.
And launch and landing. Pretty iconic now. Falcon 9 rocket splashed down in the ocean.
Usually off the coast of Florida, yeah. And you mentioned something interesting earlier, the landing system.
Right. It was originally meant to land propulsively, using its own engines, like something out of sci-fi.
Exactly. They abandoned that for splashdowns initially. But in a fascinating twist, they actually re-enabled propulsive landing capability in 2024, not as the primary method, but as a backup.
A backup for parachute problems.
Precisely. It shows how they keep iterating, adapting the design.
And those engines, the Super Gracos, they're also the launch escape system, right?
Yep. 8 of them integrated into the capsule walls. Each one packs about 71,000 newtons of thrust. If the rocket fails, boom, they fire and pull the capsule away to safety instantly.
What about the cost? How does it stack up?
Well, NASA's own Inspector General estimated it at around $55 million per seat. The actual contract values for the first few missions were maybe $60 to $67 million per seat.
And rising slightly for later ones.
Yeah, up to about $72 million per seat for the later contract extensions. Still, often held up as a benchmark for cost-effectiveness in human spaceflight.
Inside, it's very sleek. Touchscreens dominate.
Very much so. Minimal physical switches. There's also a small space toilet, which is essential for longer trips.
And that window option for private flights.
Oh yeah, the cupola. If a mission isn't going to the ISS, they can swap out the docking mechanism for this big, domed plexiglass window. Incredible views.
But reusable doesn't mean maintenance-free.
Definitely not.
Yeah.
After every single flight, the heat shield blocks this special PKAX material have to be replaced. Same for the parachutes.
Makes sense. And the thrusters.
The smaller Draco thrusters used for maneuvering in orbit. They might need cleaning or replacing too, especially after being exposed to corrosive seawater during splashdown.
There's also that unique launch prep, loading super chilled fuel really late.
Right, just about 40 minutes before liftoff for the Falcon 9. And the crew is already strapped in with the launch escape system armed.
Which is different from how NASA used to do things.
It's very different. It's faster, potentially more efficient, but definitely represents a shift in operational philosophy. Very cutting edge.
Okay, let's pivot to Boeing Starliner. Different shape, different size.
Yep. A bit wider, actually. 4.6 meters in diameter, 5.1 meters tall. And like Dragon, the crew module is reusable. Boeing aims for up to 10 flights per capsule.
But the service module is ditched.
Correct. The service module containing propulsion and power systems is expended each time. Similar concept to Dragon's trunk in that way.
Launches on a different rocket, too.
An Atlas V. Specifically, the N-22 configuration, meaning no fairing, 2 solid rocket boosters. A real workhorse rocket itself.
And the landing is a key difference. No splashdowns planned for Starliner.
That's the primary design, yes. It's built to come back down on land, using a combination of parachutes and airbags to cushion the touchdown.
Where does it land?
They have several designated sites in the western U.S. White Sands Missile Range in New Mexico is a primary one. But crucially, it could do an emergency splashdown if it absolutely has to. That provides flexibility.
Essential redundancy. What about its escape system?
Starliner uses engines from Aerojet Rocketdyne. For a launch aboard, it relies on 4 powerful RS-88 engines. Each one provides a massive 178,000 newtons of thrust. Serious power to get away quickly.
And for maneuvering in orbit.
It uses smaller thrusters, OMAC engines for major orbital maneuvers and attitude control, and RCS thrusters for fine-tuning orientation. all crucial for rendezvous and docking.
And the cost comparison here.
The NASA OIG estimate puts Starliner higher, around $90 million per seat. The contract values seem to reflect that somewhere between $91 and $99 million per seat.
That's a noticeable difference from SpaceX's numbers.
It is, and it really highlights the different development paths and maybe different underlying philosophies of the two companies. One aiming for rapid iteration and cost reduction via high reuse.
And the other maybe a more traditional, possibly more conservative aerospace approach.
Perhaps it leads to different price points, and that has big implications for NASA's budget and the future commercial market.
Okay, so let's talk about how things have actually played out, the story so far. Because it's been, well, a tale of two very different experiences.
That's putting it mildly.
Yeah.
SpaceX's Crew Dragon, once it got through its test flights, Demo 1 uncrewed, then the big one, Demo 2 with Bob Behnken and Doug Hurley.
That return of American astronauts launching from American soil, huge moment.
Absolutely huge. After that, Crew Dragon really hit its stride. The first operational mission, Crew 1, launched smoothly in November 2020.
And they started reusing the capsules pretty quickly, too.
Very quickly. Crew 2, in April 2021, was a major milestone. First time they reused not just the capsule Endeavour, the same one from Demo 2, but also the Falcon 9 booster.
And since then, it's been pretty consistent.
Remarkably so. SpaceX has been launching NASA crews regularly, basically taking over all the U.S. crew rotation flights. They've received contract extensions now for a total of 14 missions.
14. That secures ISS access through 2030, right?
Exactly. It ensures NASA has that transportation locked in.
And don't forget Cargo Dragon. It's not just people.
Right. The cargo version, under the CRS-2 contracts, has been a lifeline for ISS resupply. And it's unique. It's the only currently operational cargo vehicle that's reusable.
And it can do more than just carry stuff up and down.
Yeah, it has cool features like extend the lab, providing extra power for payloads. And just recently, November 2024, it showed it could actually reboost the ISS orbit itself.
That's a new capability. And looking even further ahead.
A Cargo Dragon variant is actually the plan for the U.S. deorbit vehicle, the thing that will safely bring the ISS down at the end of its life, around 2030. So that design is really proving versatile.
Okay, so that's Dragon's story. Consistent success, expanding capabilities. Starliner, however.
Starliner's journey has been, well, much rockier. Significantly more challenging. It was originally supposed to fly operational missions way back in 2017.
Then 2018, then 2019.
Exactly. A series of delays. And some pretty serious issues cropped up along the way.
I remember that first orbital flight test, OFT, back in 2019. That didn't go to plan at all.
No, it was quite concerning. Major software problems with the mission timer meant it burned too much fuel after launch. It couldn't reach the ISS.
NASA didn't mince words. They called it a high-visibility close call.
They did. It required a whole second uncrewed test flight, OFT-2. And even that got delayed significantly because of problems with propulsion system valves, stuck valves.
OFT-2 finally flew in May 2022 and docked successfully.
Yes, that was a much-needed success. But then came the crewed flight test, the CFT, with astronauts Butch Wilmore and Suni Williams.
Launched June 5th, 2024, but it wasn't smooth sailing either, was it?
Far from it. During the flight to the station, they discovered multiple helium leaks in the propulsion system, and several maneuvering thrusters failed during docking approach. Serious issues.
Which had a massive impact. The crew didn't come home on Starliner.
No, that was the crucial decision. After analyzing all the problems, NASA decided it was safer to bring Starliner back empty, uncrewed.
And the astronauts, Butch and Tsunami.
They ended up staying on the ISS much longer than planned. They eventually joined the SpaceX Crew 9 mission when it arrived in September 2024.
And came home with them in March 2025, a very roundabout trip.
Extremely. And the upshot is, Starliner still hasn't received its final certification from NASA for operational flights. Those are now projected for 2026 at the earliest.
Wow. That really underscores the value of having redundancy and international partners.
Absolutely. That seat-swapping agreement between NASA and Roscosmos has proven invaluable.
Where they trade seats on Dragon and Soyuz.
Exactly. It ensures there's always at least one American and one Russian on the station, maintaining that international partnership, even if one side's vehicle is grounded.
That started with Crew 5 in 2022, right? Anna Kikina flew on Dragon.
Correct. And that agreement has now been extended through 2027. It's a pragmatic safety net.
And we saw the direct ripple effects of Starliner's delays recently. Crew 8 had their mission extended.
Yeah, and they actually had to rig up 2 extra sort of makeshift seats in their Dragon capsule, just in case it needed to serve as an emergency lifeboat for the Starliner CFT crew.
And Crew 9 launched late.
Right. Crew 9 launched with only 2 NASA astronauts instead of the usual 4, specifically to leave room to bring Butch and Suni home from the CFT mission.
It really shows how interconnected everything is up there. One delay impacts everything down the line, a complex orbital dance.
It really is.
So we've got the hardware, the missions, the ups and downs. But this next part I find absolutely fascinating, the different philosophies behind astronaut training.
Ah, yes. This is where you really see the old space versus new space contrast come alive.
And JXA astronaut Kimiya Yui, who's flown on Soyuz and is training for Crew Dragon now, he apparently summed it up really well.
He did. He basically said, in Russia, for Soyuz, the philosophy is learn the physics behind it. They want you to understand the deep engineering principles.
Like his microwave analogy.
Exactly. In Russia, they teach you the electromagnetic science behind the microwave.
Mm-hmm.
On Crew Dragon, he said, it's more like just press this button, set the timer.
That's a stark contrast.
Yes.
So the Soyuz, the old space way, it's intense.
Incredibly rigorous, very technically demanding. Astronauts, or cosmonauts, are trained almost like mechanics as well as scientists. They need to master manual controls, understand complex systems.
Like the Soyuz itself, with its 3 separate modules.
Right. Orbital module, descent module, service module, or the Kerar automated docking system. They trained extensively to take over manually and dock if the automation fails. Because sometimes, historically, it did.
So it's partly driven by the hardware design?
Partly, yes. Soviet and Russian hardware often featured intricate mechanical systems. The training reflects that, and also a legacy of, Soviet ideals, courage, discipline, deep technical mastery, stemming right from the Gagarin Cosmonaut Training Center.
Okay, now contrast that with Crew Dragon, the new space approach.
It's almost the polar opposite in philosophy. The focus is much more on practical operation, using intuitive touchscreen interfaces, managing procedures.
Because the spacecraft does most of the work.
Largely, yes. Crew Dragon is designed for high autonomy. It flies itself, it docks itself, it monitors its own systems. Ground control handles the majority of troubleshooting remotely.
So the astronauts train mainly for, emergencies, off-nominal situations?
Pretty much. Training for those just-in-case moments when manual intervention is needed. But the day-to-day flying, mostly automated.
Doug Hurley, who flew Shuttle and Dragon, he talked about this difference.
He did. He said the shuttle required constant pilot input, managing thousands of switches and systems. Felt like actively flying it all the time.
Whereas Dragon?
He described Dragon as much more automated, a cleaner crew module, less interaction needed from the crew during nominal flight. He likened switching between them to a pilot learning a totally different type of aircraft.
The fundamental job, getting from A to B safely, is the same, but the how is radically different.
Exactly. The cognitive load is shifted, less on manual flying, more on systems monitoring and procedure execution.
So what's the big implication here? Why does this shift matter?
Well, the goal of the new space approach is really about efficiency and accessibility.
Making it easier for more people to fly.
That's the idea.
Yeah.
By automating more, by making interfaces more intuitive, you potentially lower the barrier to entry. You don't necessarily need to be a test pilot or an aerospace engineer anymore.
You could be a career scientist, a doctor.
Even potentially civilians on private missions. It opens the door to a future where space isn't just for the traditional astronaut corps. It's about democratizing access to orbit.
Which is a profound change. Okay, looking ahead then, the journey continues. What's next on the launch pad?
Next up for C3P is Crew 11, currently scheduled to launch no earlier than July 31st, 2025.
And it's flying on a veteran capsule.
Yep, Crew Dragon Endeavour. This will be its 5th flight, really proving that reusability concept.
And the crew for this one sounds incredibly diverse.
It really is. You've got NASA astronaut Zena Cardman commanding. It's her first space flight, and her background is fascinating geobiology, geochemical cycling, perfect for Earth science from orbit.
Then Mike Finka, a NASA veteran.
Oh yeah, Mike Fink. This will be his 4th trip to the ISS. He's logged over 380 days in space already. And critically, he was deeply involved in testing both Dragon and Starliner. Huge experience there.
Who else is flying?
JXA astronaut Kimiya Yui is back for his 2nd trip. He actually holds the distinction of being the first Japanese astronaut to capture one of their HTE cargo vehicles using the station's robotic arm. Precision work.
And completing the crew.
Roscosmos Kosmon Oleg Platonov. It's his first spaceflight, and he comes from an engineering background. So a great mix of experience and expertise.
What will they be doing up there? Sounds like a busy mission.
Very busy. Lots of research, tech demos, standard station maintenance, but some really interesting specifics too. They'll be doing simulations related to lunar landings, feeding into NASA's Artemis program, testing ways to protect astronaut vision on long missions, studying how microgravity affects plant cell division.
Wow, fundamental biology.
Yeah, and even looking at how microgravity impacts bacteria-killing viruses, which could have medical applications back on Earth. Plus, trying to produce human stem cells and even on-demand nutrients in space.
That's a packed science schedule.
Absolutely.
Yeah.
And besides the science, their time in orbit will be full of traffic management.
Welcoming new arrivals, saying goodbye.
Exactly. They'll see a Soyuz arrive with new crewmates, another Soyuz depart, plus overseeing dockings of cargo Dragon, Russian Progress cargo ships, and Northrop Grumman's Cygnus. It's a busy port.
And here's a cool piece of trivia. Crew 11 will actually be on board the ISS when it officially passes 25 years of continuous human presence.
A quarter century. That's an incredible milestone. Really speaks to the power of that international collaboration and the ongoing scientific drive.
It really does. So that kind of brings our deep dive on the Commercial Crew program toward its conclusion.
It's been quite a journey, hasn't it?
Yeah.
Seeing this massive evolution in how we get humans to space.
Yeah, that shift from purely government-run missions to these commercial services, driven by innovation, reusability.
And definitely punctuated by some unexpected challenges and setbacks along the way. It hasn't all been smooth sailing.
No, certainly not for everyone, but what really stands out is that paradox we talked about, the philosophy clash.
Right, that fundamental difference in how humans interact with the machines taking them to space. The old space, deep technical mastery versus the new space, automated oversight.
It leaves us with a really interesting thought, doesn't it? As this technology keeps advancing, as automation gets even better, what does it really mean for the future of space exploration?
Does it free up astronauts? Allow them to be purely scientists, explorers, focusing less on the flying and more on the doing once they get there?
Or does it create a need for a different kind of astronaut, maybe more of a systems manager, an expert in overseeing complex autonomous systems, someone who understands the software as much as the hardware?
It's a fascinating question. How will this shape not just who goes to space in the decades to come, but what their fundamental role is once they're out there?
A question that I suspect will keep evolving with every single mission, every new deep dive into the final frontier.